Hi, and welcome to this Anritsu video podcast. This is part 2 on the topic of RF interference and how to find it. My name is Johan Wallblad and I work as a field application engineer at Anritsu. This is the agenda of both parts of this video podcast. Part 1 is the introductory part, where we address questions like, why do we need to care about RF interference? How do we define RF interference? What are some of the common causes to it? And what do we observe in the real world? So if you missed part 1, I encourage you to check it out as it lays the foundation of what I will talk about next. In this part, I will go deeper into how to hunt for interference, which features on the test equipment that are useful, and what equipment Anritsu can provide to detect and hunt for interference. With radio interference, you often react to reports coming in on key performance indicators or KPIs. For cellular networks, some example KPIs are the number of dropped calls or poor uplink or downlink throughput. As a technician, the first thing you normally do with your test equipment is to act as the radio receiver experiencing problems. So, for cellular, it's very common that you connect to the receiver antenna at the base station. This way you will see all the signals that the real radio receiver picks up. In such a case, it's important that you connect the test equipment after the RX preselector or bandpass filter. If you don't have access to the radio's own filter, you need to connect a similar one that you bring with you. You need to do this in order to eliminate any strong side emissions. Remember, you want to act as the normal radio receiver, but it's also important to protect the test equipment against very strong incoming signals. If instead of cellular, this is some broadcast communication, such as FM radio, you need to measure in the area where the complaints were made. Nevertheless, it's always important to use an RX preselector, either the filter of the actual radio receiver or a standalone filter that is very similar. You then see the same receive pattern as the radio and can get a visual ID on the interfering signal. When you come that far, you use the various features of the test equipment to characterize the interfering signal as much as possible so that you'll know it later. We will go through some of these equipment features later in this presentation. As a first note, it's very important to understand that the interfering signals don't need to be on your receive channel. They only need to make it through the receiver filter, the preselector. Signals making it through the preselector affect your receiver's front end, causing a reduction in sensitivity and apparent lower carrier to interference ratio. This is usually referred to as receiver desensitization or blocking if it's severe. These concepts were discussed in part 1 of this video podcast. As I mentioned earlier, when you have a visual ID of what you believe is the interferer causing problems at your receiver, there are quite a few basic features you want from your test equipment to further characterize it. First, you have the basic signal parameters, such as center frequency, where you can use a marker to read out what that is. Occupied bandwidth, which is a function to automatically calculate the interferer's bandwidth. You can tell a lot from knowing this alone. Then you have channel power, which is a function to calculate the integrated channel power of the interferer. Another example is the ability to get a picture of the envelope or shape of the interfering signal, for example by using trace features like max hold. Modulated signals have distinctive shapes, and with experience and building a library of known signals, you will be able to identify signals just from their shape. Secondly, time-based characteristics can offer further insight into the interferer behavior. For example, if the interferer is pulsed, knowing its pulse duration and pulse repetition frequency will offer more clues to finding its source. Then you have location-based parameters, like time and GPS coordinates. For instance, it may be that the interference is only seen at specific times. If you then measure and keep records over a longer period of time, you may be able to see a pattern emerge. Being able to get a spectrogram view is another way to get time-based information. One nice example I have is from the US, where interference occurred in an area for a few hours every Sunday. Once this time pattern emerged, the source was finally found to be the wireless microphone used by the local church minister. It's also important to make a record of the weather conditions when the interference is occurring, or what the propagation environment is like where the interference is detected. As explained in part 1, signal propagation properties vary depending on weather as well as the environment. If, for example, your interfering signal is from an adjacent cell site and you're in a rural area, the transmitted power of that site may have to be reduced, or the tilt of its antenna may have to be adjusted to reduce its reach. Finally, signals may be linked to other signals. What you want to do is look for signals that turn on and off. Also, you want to look for carriers that turn on and off when your interference turns on and off. For example, the interference could be harmonics or PIM from a specific carrier. The most fundamental display when hunting for interference is the standard spectral display, showing amplitude over frequency. The standard trace operation feature of spectrum analyzers is max hold. That is important in detecting short duration signals or looking for an elevated noise floor. Typically, you can simultaneously show up to 3 traces, each in a different mode. You have the normal or write mode, which is simply rewriting the trace for every sweep. Then you can show max hold at the same time, which is good for finding short duration transmissions. You can also show min hold, which is good for finding, for example, a permanent continuous wave signal hidden inside a spectrum full of bursty LTE or WLAN transmissions. A dual trace display feature can also help to show what's happening. For example, simultaneously showing the standard amplitude versus frequency display and a spectrogram. Other nice features are trace hold and the ability to recall traces. Trace recall allows you to save a trace to analyze it at a later time. Many signals are bursty, which means that they are only on for 50% of the time, or even less. Some examples of that are Wi-Fi, LTE, and Bluetooth. Anritsu handheld spectrum analyzers have a burst detect feature. This comes in handy when you search for bursty signals. Burst detect is another trace mode that can detect pulses as narrow as 200 microseconds reliably. This is very useful for direction finding, making it a lot faster. Direction finding is when you use a directional antenna to find the direction from which the interferer is coming. A spectrogram, or waterfall view as it's also called, can be extremely useful when analyzing signal behavior. This shows frequency on the x-axis and time on the y-axis. The signal amplitude is shown using colors. You can see examples of spectrograms in the pictures on this slide. Commonly, the color scheme is going from blue to red, with blue indicating very low signal levels or noise, and red indicating very high levels. The spectrogram is particularly useful when interfering signals pop up very rarely, let's say for a few minutes or hours once a week. You can then put the measurement equipment at some appropriate location and leave it to record the spectrogram. If the equipment has remote control capabilities, which all Anritsu handhelds have as standard, it becomes even more useful. It's also very useful if the spectrogram can operate in zero span mode. This slide shows you an example of what I just mentioned, a spectrogram in zero span mode. You can then figure out if you have multiple signals operating at the same frequency but with different timings. That is, they have different pulse durations and pulse repetition frequencies. Finally, if your spectrum analyzer also comes equipped with demodulation or signal analysis capabilities, you can dig out even more information. If your interferer is some common source, for instance if it's a cellular network base station or professional mobile radio transmitter like Tetra used by emergency services, you can then demodulate the signal and find its cell ID and color code. This enables you to find the network owner so that you can contact them to let them know they have a problem. All Anritsu handheld spectrum analyzers are also signal analyzers, with options to decode a wide range of radio standards. If the interfering signal is not known, meaning it's not common and therefore there is no built-in analysis of it, you may be able to capture the IQ data. That is, if the instrument supports it, which most Anritsu handheld spectrum analyzers do. The captured or recorded IQ data can then be post-processed in standalone tools such as MATLAB. You can also replay the captured signal using, for example, the Anritsu benchtop spectrum analyzer, MS2830A. Now that you have characterized the interfering signal at the cell site or where the complaint was made, the next step is to start localizing it. The Anritsu Mobile Interference Hunter is the system solution that will help the user do this more easily and quickly. The Mobile Interference Hunter is a very handy tool when it comes to hunting, for example, rogue or bursty signals. It really shines in multi-emitter scenarios, such as leaky cable TV systems. It can also be used to simplify work required to clear spectrum for new usage. Some of its key capabilities are that it's 5G ready up to 110 GHz using Anritsu's ultra-portable spectrum analyzer MS2760A. It comes with a guided area scan mode where the user is guided to a geographical area that could use more data points in order to reliably determine the most likely location of the signal source. It also supports post-capture analysis, whereby the drive data is saved for post-processing. The user can then modify search parameters, such as violation limits, without having to redrive the route. Anritsu's patented algorithm and the fact that you're taking many measurements per minute and averaging them while driving solves issues with RF reflections, shadows, and multipath. In traditional interference hunts, where you use a spectrum analyzer with a directional antenna, these issues can lead the most experienced user astray. It's also very easy to set up and doesn't require a specially equipped van. Pretty much any car will do. It also comes with voice prompts, making the drive easier and safer. One person can easily do this job alone. As I mentioned earlier, the traditional way of doing direction finding or interference hunting is with a spectrum analyzer and a directional antenna. In a drive test, this means stopping at some location, get out of the car, find the interfering signal and take a bearing. Also, you would need to spend some time in each location as you have to deal with multipath reflections or RF shadows. Maybe you can manage to make 10 or so measurements per hour. With the Mobile Interference Hunter, you will instead make hundreds of geolocated measurements per hour while you're basically only concerned about driving the car. This is what a typical setup would look like. You don't need physical access to the Anritsu handheld spectrum analyzer, so this can be placed in the boot. Instead, you connect the instrument through an Ethernet cable to a small WLAN router. On the dashboard, you then mount any Windows-based tablet where you run the Mobile Interference Hunter software. The tablet connects to the Spectrum analyzer through the WLAN router. You then place a mag-mount omnidirectional antenna, including a GPS antenna, on the roof of the car and connect this to the analyzer. Also, if you need to make any changes to the instrument settings, you don't need to get out of the car and open the boot. All Anritsu handhelds come equipped as standard with a built-in web server. So, using the tablet's web browser, you will have complete control of the Spectrum analyzer. The Mobile Interference Hunter really shines in complex situations. I mentioned it already, but in general, the fact that so many measurements are made eliminates the problems with reflections and multipath and shadowing that you face in traditional ways of direction finding. Also, since the Mobile Interference Hunter uses channel power for its measurements, means it can deal with signals that wander in frequency, such as oscillating cell phone repeaters. Furthermore, the Mobile Interference Hunter software allows you to use many of the standard spectrum analyzer features to simplify the signal hunt. For example, if your signal is somewhere where there is a lot of LTE uplink traffic, you can use min-hold to ignore all the LTE bursts. As I already mentioned, Mobile Interference Hunter uses channel power measurements, so you know immediately when the signal stops. You can also use max hold or burst detect to capture bursty signals. The Mobile Interference Hunter software comes with Anritsu's patented driving direction guidance. In the beginning of the drive, you'll be in the guided area scan mode. You can see an example of that in the picture at the top. The blue areas indicate that you need to drive there to gather more data. Once you've done that and the scan is resolved, a heat map will be generated, showing you the location of the interfering signal. Now, once you're done with the Mobile Interference Hunter, you have a pretty good idea of where your interfering signal is coming from. In order to be able to tell with even greater precision, you will need to get out of the car and do more traditional direction finding. And more importantly, the Mobile Interference Hunter will indicate where the channel power is highest at street level. If the signal is coming from a tall building, you will need a directional antenna in order to pinpoint its source. The Handheld Interference Hunter from Anritsu is very user-friendly and light, and you can operate it with one hand. It comes with a built-in electronic compass, GPS receiver, and preamplifier. It has a trigger button for saving bearings. And no special tools are needed for attaching antennas, and it connects to the instrument via a USB cable. This slide just shows you the various pieces you need for the complete setup. First, you have your MA2700A Interference Hunter, and with that you need some directional antenna, be it Yagi or log periodic. It's also easy to attach a bandpass filter between the antenna and the interference hunter. Anritsu has plenty of such filters as accessories. Finally, you need a software option on the Spectrum analyzer called the Interference Analyzer. After that, you're good to go. As part of the Anritsu software toolbox, you'll find Easy Map Tools. This is a PC software that allows you to download maps for offline use. You can then copy it onto a USB flash drive, plug it into the Spectrum analyzer, and use the map directly in the interference analyzer mode of the instrument. You can also take bearings without a map on the instrument and import the saved data to a map on your PC at a later stage. This is an example of what this looks like. For example, measured KML data can be imported into Google Earth as shown in the picture on the right. Now, we've gone through the usual steps of locating an interfering signal. We have measured at the receiver antenna of the cell site or in the complaint area. We have found the area where the interferer is the strongest by doing a drive test with the Mobile Interference Hunter. And then we have pinpointed the interferer's location with the Handheld Interference Hunter. There is a complementary tool that you may want to use or need to use before you go through all that. Or the area is of such importance that you must be able to react very quickly to any RF interference, such as near an airport or harbor. These are cases when you need to monitor the spectrum for long periods of time or even permanently. Anritsu's remote spectrum monitor makes this possible. We'll talk more about it in a minute, but the remote spectrum monitor and its vision software is really built to handle big data. This allows you to monitor signal activity continuously and look for patterns of unwanted activity over extended periods of time, define limits and automatic alarms, and locate interfering sources. Before moving on, I also need to mention that this can also be used to characterize spectrum occupancy. Government regulators and operators are often interested in determining the usage rate for various frequency bands. Monitoring these frequencies provides the information needed to optimize spectrum for maximum utilization. Spectrum monitoring is also used to uphold government regulations. Police, firefighters, air traffic control, military, and emergency services must all have access to communications that are free of impediments and distortion. Compliance with spectrum regulations is often enforced by spectrum monitoring. You can see what such a monitoring system can look like in these pictures. You position multiple remote spectrum monitor hardware as probes, covering a wide geographical area. One example of where this is useful is when monitoring for illegal radio transmissions from a prison facility. The probes are connected over a network to a monitoring center where the Anritsu Vision software platform is used. We'll talk more about that in a minute. The remote spectrum monitor family has 4 members that all have a maximum frequency of 6 GHz. You have the one-port half-rack MS27101A, then the outdoor version in the MS27102A, and you can get this with 1, 2, 4, or 6 RF ports. Then there's the MS27103A full rack instrument that's available with either 12 or 24 ports. And lastly, there's the OEM module, which you can integrate with your own product. The Vision software platform works with Anritsu's spectrum monitoring hardware to automate the process of collecting measurement data, as well as providing useful information about network health and use of the spectrum. Using multiple hardware probes covering a wide area, the Vision software presents a comprehensive picture of spectral activity to assist users in monitoring the spectrum for unusual activity. The Vision software at its core is built for big data, so naturally there's a database at the center of it. The software consists of 4 main parts where the database creator is used to define the database. This entails, for example, listing all the probes with their network addresses or IP addresses and their GPS coordinates. It also allows you to define frequency bands to monitor and basic spectrum analyzer settings per band, such as resolution bandwidth and video bandwidth. Vision Acquire is then the engine where you define how often each probe is swept, who should be notified with alarms when limits are violated, and where the database is stored. Vision Monitor and Locate are then parts of the software front end. In Vision Monitor, you can look at spectrum traces and spectrograms for each probe and scroll back in time to look for suspect activities. This is also where you can define limits that will be used to trigger alarms. Vision locate is a map view where you can locate the source of a signal that you've marked in a spectrum trace through triangulation. Naturally, you need at least 3 probes for this to be possible. And the underlying techniques to locate signals are either power of arrival or time difference of arrival. We'll talk more about those later. This slide shows more of what you can do with Vision Monitor. I won't talk too much about it other than to say that limit lines or masks can be edited and applied retroactively to historical data. The upper right-hand picture shows how trace data for multiple probes can be viewed with either synchronized historical data or live data. You can also use it to create pass-fail reports. As I mentioned, one of the techniques used to locate a signal is power of arrival. It requires at least 3 probes to see the signal. The location of the signal source is estimated based on the power measured at each probe. The other method is time difference of arrival. The major drawbacks of power of arrival are that it's affected by obstacles, as it's based on a measurement of power, and it's limited to being able to detect signal sources that are inside the triangle created by the probes. On the positive side, it's useful anytime and for any signal that you can measure. Time difference of arrival, on the other hand, is minimally affected by obstacles, and it works outside the triangle. It's also much more precise when it works, and I'll elaborate on that a bit. Time difference of arrival, rather than power, uses the time that a signal arrives at each probe. Based on the measured time difference, a calculation is made for the interference position. You can imagine that for this to work properly, all the probes need to be very precisely synchronized. It's not enough that the probes detect RF from the same source. They must capture the same signal in time at each probe. The captured signal is then shifted in time to align the measurements for all probes, and the shifts required are used when calculating the interference position. That brings me to the main drawback of time difference of arrival. In order to time align the received signal, it must contain a non-random, non-repeating structure. That's not the case with many interference sources emitting white noise or sine waves. Then there's no means of distinguishing a correct time shift. Modulated signals, on the other hand, do contain an internal structure that can be aligned in time. Therefore, time difference of arrival is only useful for modulated signals. That concludes this 2-part series on the topic of RF interference and how to find it. Thank you for listening. I hope you found it interesting.